So these examples of 54, for example, which we are going to go through, I had this list of answers without any supporting documentation. I have a start here, which this person didn't finish the assignment, but I know what they're thinking, and I know how to help them get from where they didn't finish to the next step, because I can see that. Does that make sense? And that's important to me, even if they didn't finish it. This one just says 86,000. How am I going to go from that? How do I go from that to something else? So I need more, even if you don't know what the problem, even if you don't know where to start, I need more. And again, I don't need you to write verbatim all the word problems out. I just need more. So 54, this one, obviously this is like a great example of working all the steps out. But I can see the complete process. There's even units here. And you don't need this to get a 10 out of 10 on your homework. You should be going for that, right? But even this gets 10 out of 10 on the homework. This shouldn't. Because I can't develop anything from just that one number. So when I start to ding you on your homework, because I didn't do it here if you wrote something. If you skipped it problems entirely, I might have given you a 9 out of 10. But for future, I'm going to ding you if there's nothing that you can work from. Does that make sense? So I'm trying to lead you to where I want you to be. I get that sometimes you may not know how to do the homework, which is why I don't grade it for accuracy, but I need you to be working to try to get to the answer. Does that make sense? Okay. All right, so that's my little sidebar there. Let's go to much better. Okay, so, all right. I'll go back to the odd ones in a second. I do want to go through these evens because I didn't actually finish writing out my solutions. But here's 20. I asked you to write it in point slope form. So in this case for number 20, you were given the slope, and Caroline asked a minute ago about the section which we sort of skipped. I don't necessarily need to go back and tell you what it means to be parallel or perpendicular, because that's a topic that you know from Algebra 1, and I'm sure that you covered it again in geometry with various shapes and perpendicular things, right? So perpendicular is opposite reciprocal slope, and I made myself a little note for y'all so I wouldn't forget. Parallel means the same slope, and you should be able to take the y equals mx plus b format that they gave you and pick out slope really quickly. So in 20, we were supposed to have parallel slope, so I wrote down the slope that I need, and then that formula is very easy. It's y minus the y value, and then x minus the x value, so opposite math for both of them, and then put the slope there. And I was done for 22. In 22, just to write it so you can see it, because I did skip those sections, so I'm giving you a little bit more here just to make sure everybody's good. I'm looking for y minus 8 equals parallel, so same slope. This is my little note that meant parallel. So 3 is what I'm using, and then x minus 2. Here for 24, it's a little bit different because I'm looking for perpendicular, and they told me y equals 2, negative 2. Y equals negative 2, so I have to know what that is. And for you, in an honors class, it's totally okay if you forgot, but then you take your book. This is me looking through the book. You can't see this on your video. But, you know, look back and see what parallel and perpendicular means, or y equals, what line that is, in case you're not sure. Take your calculator, type in y equals negative 2, see what it looks like. Question? Or just, okay, you can just sit like that. Yeah.
I just had a question on like how you would write the equation.
For the next one? For this one. Okay, so first you had to know what this looks like. That's what I'm kind of getting at. And if you forgot, then you look it back up. You try to graph it on a calculator. It looks like a horizontal line that crosses at -2. It crosses the y-axis. That doesn't look like a y. Now it does. Crosses the y-axis at -2. And y equals lines have slope that's 0. And that doesn't help me for this equation because I need it to have undefined slope. That's the opposite of putting 0. You can't say you're not allowed to go slope is 1/0. So what do you do if it's 1/0? What's that slope? It's undefined. So yeah, it's a vertical line instead. So if you can draw it, number one, you can visualize the perpendicular. So I need it to be a vertical line that goes through this point. Where's that point? -6, 2. Pretend it's right there because my image is very small and that's scale. So if I need to be perpendicular, I can visualize it as perpendicular. And now which axis does it cross? It crosses the x-axis now. So my line needs to be x equals, and where does it cross the x-axis? What value from this point? Which of these is the x? -6. So that one, not as straightforward as 20 and 22. For me. For some of you, it might just click and you might be able to do it. For me, I actually do need to think about a drawing. That helps me a lot. So this slope is undefined, and you can't really see undefined slope anywhere in here. That's why I need to draw it. Does that help you to write the equation? So I'm not sure how Mrs. Hopkins teaches how you remember vertical lines versus horizontal lines, but I think it is helpful to say that this crosses the y-axis. I don't know where the video cut out, but here's 46, and we're talking about 50. All right, so 50, if you're completely stuck, you can write down the important information from the problem. This is what I'm looking for. They told me the car costs $6,500. The cost per month is $350. How much am I going to spend on the car? My total cost will be the amount I paid for it, plus I spend $350 a month. They must drive a lot. That's a lot. And then I get this, my cost, and I wrote it in function notation. My cost per month is going to be $6,500, and you could have totally used an X or whatever you wanted to put there. G for gas, I don't know. But there's my problem for 50. Yeah, good? Okay. That's a straight up kind of modeling problem. Then we're looking at 54, which I had several people ask me about. And this is how I would set up 54 upon reading it. They told me I had 2 buildings. One of them was $21.75 per square foot. So I wrote foot squared just because that's the easy way to write it in math. Building 2, $17. Total dollars budgeted. They told me that. And of course, I mean, I'm a math teacher, so I did sort of set it up so it looks like an equation, but let's do an aside for a second. If you didn't know what it meant to rent a building, and I've worked a bunch of jobs, and one of mine was to manage leases, which meant I did stuff like this. If you didn't know what this means, you do know, and I can bring this back to you going to the grocery store. If you go to the grocery store and you buy 2 boxes of Smarties, and then you buy 3 bags of mints, and then you have a total cost, it looks like this. Like every time you go to the store, right, now you have self-checkout, you're going 1, 2 of something, and then 3 of something else, and you multiply, and then you add it together, and that's the total. So even if you've never leased any space before in a building, you've bought things. So that goes back to that. So we don't know things. We don't know how many square feet we're going to rent in this building or how many in this building. And so I'm telling myself and I'm telling you by writing it down so I can follow it and you can follow it, which one is X and which one is Y. If one of the buildings was named the Kramer building, you might call it C or K, whichever Kramer spelled like, and then you could name it by building. But I chose X and Y because that's easy to follow. And they told me something else. They said, write an equation that models the possible amounts of space rented in the building. So just like this, if I thought about it as a grocery store problem, I'd say I'm going to spend $21.75 for this much space plus 17 times this much space, and that's going to be my total amount of space. And I don't need you to write it out in units, but if you look at my units, do then my units make sense? Because if you said x feet squared times 21.75 per feet squared, that's what the divide means, it's put on the bottom, and this was in dollars, look what I have money. So it also makes sense mathematically, and there you go, that's A. And I do believe that that was within your means of figuring out with not just algebra logic, but you go to the store and buy stuff logic. Like you buy things. You know how that works. So I would like for you to use that common sense in my class. That would be great. So A. If it wasn't clear before, you good now? Okay. Do you see how setting things up in some sort of sense? I don't know if that helps. Okay, B. I'm going on. How many square feet of space can be written in the first building if 2,500 square feet are written in the second building? So look, I labeled this building 2, and they told me I had 2,500 square feet here. So I'm going to put 2,500 square feet here. I'm going to put 17 here and 21.75x plus equals 8,600. And the numbers are, bigger than your average homework problem. So one would assume that you probably pulled out a calculator to work this. Did you? Okay, and that's fine, because I would too. And all mine are in the back, so I don't have one. But we have that pretty problem worked out, which I conveniently deleted just a minute ago. But you would have 21.75x, and then somebody multiply that out. What'd you get? Really? 42,500 equals, oops, there's an extra 0 there, 86,000. So we're going to subtract that from that. So now we have 21.75x equals 43,500. Is that right? Then we take our calculator again and we divide both sides. And then it was 2,000? So 2,000. 2,000 what? 2,000 bananas? 2,000, no. What is x? X is area, right? So when you go into, have you ever heard like, this is the biggest Harris Teeter we have in the whole United States? It was for a while. I think we're number 2 now. But it has, I don't know, 100,000 square feet. You didn't know that?
Wait, we're not anymore?
I think somebody built another one. Yeah,
No,
that was the model, and so then they built another one. Sorry, I didn't mean to burst your bubble.
I think we need to look it up.
I think they built one in New York.
We can look that up later. Anyway, they would talk about how big it was by how many square feet it was, right? So like big stores are 100,000 square feet. So this is in square feet. This is not bananas. This is feet squared. This is the area multiplying length times width of x. Okay, so we figured that out. So in one building, we've got 2,000 square feet, and we have more square feet in the other building. If you were leasing, would that make sense to you? Would you want that scenario? Let's use some common sense again. How come? We would want that. Why?
Because it's cheaper.
Because it's cheaper. Because we got 2,500 in the one that costs $17 square foot, and we have less. So we're maximizing our square footage a little bit by having more in the other. That's good logic, right? Okay. And then C asks something different. C says, hey, which this makes sense. What if the company wants to rent equal amounts of space in the building? So pick a store, your favorite store. Target. Okay. So what if we talked about the Starbucks in Target, because Target's not going to be 2,000 square feet, right? What if we talked about the swimwear department or something in Target, something smaller than an entire 100,000 square foot Target? So every Target, if you're trying to make them the same, is going to have the same swimwear department, generally speaking, in places near water, I guess. I should have gone back to Starbucks, but that's too big for Starbucks. Anyway, theoretically, you'd want the same, but if you were renting in New York, the rent might be more expensive than here in New Bern, North Carolina. But all of your Starbucks, or whatever that is, swimwear department, Starbucks, they need to be the same size. So this problem is saying you need them to be the same size. So we need to rent $25.75 of some amount we don't know. And then we're going to have $17 of what? Of the same amount, right? The same amount, X, because they said they're the same. And these represent area feet squared. So we use the same amount. And then we end up with 38.75. X equals 86,000. We go like this. We go like this. And we get X equals, what'd y'all get? 2,200 something? 2, then what? 19. Okay, so feet squared. So let's read the question again. If the company wants to rent equal amounts of space in the buildings, what is the total amount of square feet that can be rented? Have we answered that question yet? What do we need? What's left?
You have to multiply it by 2.
Yeah, right? Because we got some in this building and some in this building. Does that make sense? So this is for one building. And so some of you had this answer, but that's not quite the question they were asking. So I just want to make that clarification there for you. So we need 2219. Oops, I don't know why I missed a decimal there. 2219 foot squared, also in building 2. So we ended up with 38 feet squared in both. Nowhere in this problem did they ask you to graph it, but I couldn't help it. I really wanted to graph it in my head. So what I did, and that's where one of the problems, if you saw it, it said, because I'm going on now with it on the side, if everybody's clear with A through C's now. Okay, so then I got to thinking, okay, what would it look like if I graphed it? And so I guess I need everything in this picture so you can see it. Here, I'll just rewrite it right here. 21.75x plus 17y equals 8,600,000. Sorry. Okay, so one of your peers in their homework, they started this chart. I don't know how exactly they wrote it. I'm going to do 0 here and then 0 here. How's that? Okay. I think it was the other way. But anyway, same idea. So what did this chart represent? Y'all tell me. The intercepts. What did it mean, though, in terms of the building? Because that's correct. These are the beginnings of the intercepts. What does it mean in the context of this situation? Yeah. So if we had 0 for x, that means we don't have any in building 1. So we're going cheap, right? We're going Target in New Bern versus Target in New York City. I'm pretty sure that wouldn't even be their dollar amount. But anyway, so what would we get? And I think it was close to 5,000. So if we said 0 for here, I think it was about 5,000. I think I figured that out already. Did I do that? Yes. So if we divide it by 17, we got 5,058. I'm going to say 5,000 for just a round number. Is that okay? Y'all okay with that? Okay. And then if you divide the other way, we got 3,954. I'm going to round that to 4,000. 5,000. Y'all are very quiet. I don't feel like I've blown your mind yet. I'm trying to go here. So that means if I have 0, I go to 4,000, 0, I'll be at 1, 2, 3, 4,000, because I have 0 of the expensive and more square footage. No. How's that true? 0 for, did I do it backwards? Oh, here's my point. 0 is 5,000. See, this is where I need y'all to speak up. Let's hate you're crazy. You see what I did? I did my chart in my mind the wrong way. So here's my point. 0, 5,000, or 4,000, 0. And I'm trying to write it over my X and Y now, so I'm not confused. You see how I confused myself, but I fixed it? Okay. It didn't make any sense that I would have more square footage in the expensive one. So here's 5,000, and then 1, 2, 3, 4, 4,000. And so when I looked at this problem first and thought about C and got this answer to start, that didn't make any sense. But I want y'all to help me out. Why didn't it make any sense? Because the math was good. I needed X in both of them. Why would I only have 22,000 square feet if I equally split them between the two? Because there's different prices, but really my smallest value is 4,000. This is my input and output. I could have 0 square feet all the way up to 5,000. Or I could have 0 in the other one and have up to 4,000. But why would I only have 2,200 if I split the cost? That's what I was thinking. What's wrong with that? How much did I really have? Because we already talked about that. This is what I was thinking. I was thinking the cheap one got me 5,000, the expensive one got me 4,000, and if I used both, I only had 2,200. That's not cool. But what did we already figure out and see as a group? It's up there. How much?
In total, you're getting more.
Yeah, in total we have this much. So it is in the middle. Does that make sense to you? Because I'm really at here where they're equal. That doesn't look like a square, but it's supposed to. This is 2219 and this is 2219. And together, if you add them together, you get not 2,200, but 4,438, which is right in the middle between 4,000 and 5,000. That makes sense. So when I was just doing math straight up without considering context, I was confused. Because legit, I have to think about problems. I don't just go look at the answer. Am I making sense or not? Okay. If it's in context, it has to have some sort of actual meaning. It needs to make sense a little bit. So there's where we are. Okay, so way more information that you wanted about 54, but I wanted to develop that a little bit further, and I want you to think about context of the problem, because I want you to be able to answer stuff. And you don't necessarily need to take an entire page to do a problem. You saw that one person did it in about 5 lines and had lots of really good work there, and that was plenty sufficient, and I could follow everything. But not doing anything means you're not thinking, and I need you to think. It's not going to be about just these problems that have do this, do that. That's not what this class is going to be about. This class is going to be trying to figure out the math and then applying to the real stuff so that we can be real smart at the end. Okay, moving on. Pause this for a second. I think I just blew your mind. Title of this section, Model Direct Variation. And direct variation is a linear phenomenon. It means that as one thing increases, the other increases. So they're directly related to each other. So it looks like in a graph, a linear, I don't know what the word is. I'll just say graph for lack of a better word. It is a linear graph, but it will always go through the origin. Goes through the origin. Okay, so direct variation means that as one of the quantities increases, the other will decrease. And as one decreases, the other will decrease even more, if you look at it from a standpoint of around the origin. But the best way to consider it is, well, no, I'm not going to even write that down. It goes through the origin. We're going to start there. And the example I like to use and that I'll use all year when I refer back to this is allowance. And this may not be the case in your household, but generally speaking, if parents give an allowance, however they associate it, whether they just give it to you freehand, just like, here you go, here's an allowance, or whether they base it on chores that you do, theoretically, let's base it on chores. And let's say that you are the oldest child, and so you have more chores, right? So you probably, theoretically, in a fair world, get paid more in allowance. Does that make sense? You have more chores, you get paid more. And your younger sibling doesn't have as many chores. They also don't need as much money because they're younger and they don't need things like you do, going to the movies or whatever with your friends or buying gas or whatever, so they get less allowance. But let's say there's a direct variation between what you get and what they get. So let's say that if you, younger sibling, let's say that if you don't get anything, they don't get anything. That seems fair to you. Let's say that if you get $1 every week, that they get 50 cents. Let's say that if you get $2, that they get, how much are they getting so far, do you think? $1. So they're getting half as much. And if you get $4, they're getting $2. Like, that has some logic to it as far as allowance goes. So that's my first example usually. So for every dollar you get, they get half as much. There's a direct relationship. And for every iteration of this, every iteration, does that iteration word make sense to you? Every time we were to think about another example, a new example, if we put in $16, they'd get $8, right? So for every iteration, the sibling gets half as much. It doesn't vary. They don't, if you get $16, they don't get $10 randomly. It is directly related. So direct variation is going to have a consistent number associated with it. And in this case, I've made this look sort of complicated, but it's really just like X and Y. And we're looking at this example where we would say Y is equal to 1/2 of X. And it's a linear association. It looks like a line. I don't remember who asked about it. It might have been Stephen asked about it last class. How do we know that this particular equation is a line? Do you remember what my answer was?
It can be put into the linear equation.
It can look like y equals mx plus b. In this case, there's no b, and that is important. I told you this always goes to the origin, so the origin's always going to be the b. There's no b here. So note the y-intercept is 0, meaning it goes to the origin. I'm going to say that again just for fun. But the answer was that this is to the first power. Okay, lines only have the first power there. You think back to your summer packet. We graphed a lot of x squareds, and they had that parabola shape, right? So it was x squared, and they all had this shape. Lines have a first degree power, and that's what makes them linear. They don't have a 1 there, they're not linear. So this direct variation has a constant of variation. And that's the slope. If I were to graph this, if we made $1, they made 50 cents. If we made 2, they made $1. It would end up looking like this. It would go in the other direction. It would have a different meaning, meaning if you owed your family $1, a negative amount, you owed them money, then your sibling would owe them half as much. Okay? It would have that same relationship, but in the reverse direction. So this is what it looks graphically speaking. It goes to the origin. It has a slope of up 1 over 2. So that this point is a really good example of the slope, which is change in y over change in x. That's what slope is, rise over run. But we call this this value up here the constant of variation, and it doesn't change. It's always going to be the same slope, and that's what lines do. They have the same slope everywhere, right? They don't just go like this and then randomly switch to a different direction. They have the same slope everywhere. So direct variation, I've tried to talk around it a lot so that it makes sense to you, but it's an equivalent relationship between the two things you're comparing, and it's always the same. That's why it's called the constant of variation. All right, so that's me explaining it with an example. Here's the book's explanation. They say, we're going to say this is y equals a times x. And they change the m to a because we're looking for that constant of variation, and it's the same thing. It's just a different way to look at it. Because sometimes we don't know what the relationship is between the numbers, and we have to figure it out. But we're not thinking of it as a graph, we're thinking of it as a relationship. And so this would now be what we would call the constant of variation. Direct variation. Direct variation looks like multiplication, right? Do you see it? It is, and it looks like multiplication. I say that because, again, you have the PSAT coming up, and even though that's not part of this lesson, and aside over here, I'm going to tell you that there's other math that could be inverse variation. So I'm going to put this in a box after I'm done with my pretty notes here. Inverse variation, if this is multiplication, what do you think the inverse variation is? Division. So we would actually write it like this, except it's the x that's divided. So if you were to see inverse variation on an SAT problem, you might know enough to get started on it, or you might know enough to know, well, it's not this one because this is direct variation. As x gets bigger, y also gets bigger, that kind of thing. Whereas here, as one value gets bigger, the other one gets smaller. It's a different sort of relationship. And just for fun, it looks like this, so you can see the difference. Does that look like a line? So it's a different kind of relationship, and it's not a line, and that's why it's not in this section. But as an aside, if you see inverse variation, it means two things are related. Here are the two things, and there would still be some number that goes with it. So there's your aside. Okay, so how would we use this? We would say that, I'm going to start an example. If someone says to you, we have a situation with direct variation, and this point negative 4, 8 is a solution. So our situation is, I'm telling you that there's direct variation. I'm telling you that negative 4, 8 is a point for this. And above that, I'm telling you that y equals ax is the idea behind direct variation. So if this is a situation, a scenario where this is a solution, there are multiple ways to think about it. One is algebraically, I can use this equation and figure out the constant of variation. How can I do that? What's my equation? Up at the top of the page, under the numbers. Yes, looks like yaks, right? Yaks. That's my equation. Here we go. Y equals a times x. I have two of those values in this particular example. What do I have? What's been given to me? It's like a gift. The x value is negative 4. The y value is 8. So of these 1, 2, 3 things, somebody's given me two of them, which means I can find the third thing. How about that? Yeah? Okay, so let's do that. I'm going to put 8 for y. I don't know a yet. I'm going to put negative 4 for x. Parentheses are important in this case. For the time sign, somehow you need to make sure it doesn't look like subtraction because it is a multiplicative thing happening with direct variation. So how much is a? A equals negative 2. So everybody agrees with that. That's good. That's my first sort of note in there. Yeah. So I found a. I'm going to be looking for the actual direct variation equation that relates all things in this situation. So the actual y equals ax formula needs to be translated into y equals negative 2 times x. And this is a more important, and it's going to get a bigger box, a more important part of my solution here because this represents all of the direct variation, all direct variation that satisfies negative 4, 8. So we used the point, we found the constant variation was negative 2, and we could use it to find something else. What is, so A, find the constant variation. We did that. So B, this is the y equals negative 2x, all, that looks like it's running together. Let me write it better. All, it models all situations. And C, what is y if x equals 6? What is y if x equals 6? Negative 12. So we have the one that models all of the situations for this particular scenario. Not all situations for all time, but in this scenario, in this family with allowance or whatever it is, this is probably not a good allowance scenario. But anyway, we could go, well, I know that y equals negative 2 times x, so then y must be negative 12. And so we were given negative 4, 8, we found another one. We found 6 and negative 12 as another point in that same scenario. So we were given x equals 6. We found what the y is. And because we have x and y, we can also write it as a point. I'm just trying to round out all of my answers there. And then I could graph this without knowing anything else. Because what's the other piece of information that I know about graphs of direct variation? They go to the origin. So you could actually also we could graph it. We could say it goes to the origin and then negative 4, 8. So that's 1, 2, 3, 4, and then 1, 2, 8. Here we go. There's the direct variation picture that represents that. And every point on that line also satisfies the equation y equals negative 2x. If I went to this point, I would go down 2 over 1, down 2 over 1, and that's the same slope everywhere. So it satisfies all of those things. So direct variation, in my example, it probably sounded more complicated than it is. It's simply y equals a times x, and it has the same little change in y over change in x down everywhere. The relationship is the same. That ratio of change is the same. So let's do one more where you're just finding just the math part, okay? Just straight up math. Let's do that. So I'm telling you in this example 2 that we have direct variation. Direct variation. Is this showing up? Yes. And so what needs to happen, I'm going to have direct variation between y and x. What needs to happen is you need to go direct variation. That's y equals ax, and so that's the first thing that you write down. Direct variation. And we'll give you another random point. Let's say that the variation is 4, negative 5. If a point 4, negative 5 satisfies this situation, find x if y equals 2. So you're told direct variation, you're given a point, you're supposed to find x if y equals 2. You have to find out how they relate to each other first. Your goal number 1 is to find a. So everybody take a second, find what a is given this point. 1, find a. 2. So got a little cheat sheet at the top. We're going to find a. We're going to use a to write a general equation. And with that general equation, we can find another point or more points. So I'm going to give you a second to work on that. We'll come back. A we found was negative 4 over 5. So y equals negative 4 over 5x. We're supposed to find x if y is 2. So we put a 2 here. Negative 4/5 x. So just to finish this out, because it's a fraction, sometimes y'all are a little bit like freaked out by fractions. What am I need to multiply both sides by to make negative 4/5 go away? Negative 5 over 4. So sometimes people will like to divide because they see that as multiplication. That's just messy. Instead, let's multiply by negative 5 over 4. I don't know why I wrote it with the parentheses quite like that, but there you go. That cancels. So x equals negative 5 over 2. Yeah? Yeah? Okay. So then I have a new point, which would be negative 5 halves 2 points. That would be like, I need these two things. I need the general equation and I need my new points. So you've got some homework that's pretty much like that. Now let's go back to an example. Yes. Did I do something wrong?
I got negative 5 over 4.
Did I say it backwards? No? Okay. Okay, so let's see. So speaking earlier would be great. Because it's totally possible that I just hear things and write them down in the wrong order. It's totally fine either way, because I definitely I'm not always dyslexic, but I think I do write things backwards sometimes. So let's just see it. What am I doing? I'm doing y equals ax, which means 4 goes here and -5 goes here. So that's handy, right?